They will envelop the Earth. Friction with those gases will cause this once blue world to gradually spiral home, melting into its mother sun. This battle between energy and gravity repeats in every corner of a galaxy like ours, with gravity drawing gas clouds into stars. The stars will burn themselves out on a wide variety of timescales, depending mostly on how large they are. They'll leave remnants that grow slowly cooler. As a result, galaxies like ours will grow dimmer over time, unless they get seriously stirred up. That's what's going to happen to our galaxy. At just about the time our sun begins setting its sights on swallowing Earth, any remaining inhabitants here will see the stars of the Andromeda Galaxy looming above the plane of our Milky Way. As shown in this simulation, the two are likely to tear each other apart, or at least severely jumble each other up. If it's a direct hit, all the stars in both galaxies will gradually join together in a gigantic galactic puffball known as an elliptical galaxy. All this turbulence of the merger could stimulate a wave of new stars being born, reinvigorating this new, larger galaxy. Dust-ups like this, where galactic neighbors come together, will be common as the epoch of stars grows toward its later stages. But a wholesale thinning out of the universe is inevitable on a grand scale. Recent studies of the cosmic expansion rate show that the universe is in no danger of succumbing to gravity. It won't all end in a big crunch. In fact, over the last 6 billion years, it's begun to accelerate outward, as gravity begins to lose its grip on the universe to an unseen force called dark energy. You can see evidence of this now, out in the huge voids of space between clusters of galaxies. Think of the voids as ever-expanding bubbles. Where the bubble walls touch are filaments of galaxies. As the bubbles grow, these filaments will stretch and break. The distances between galaxies will widen at a faster and faster pace. Eventually, most observers will see only a few isolated clusters of galaxies huddled together, with little connection to anything else, and few clues as to how they got there. A good place to be, in those long twilight years of the stellar era, would be a place where gravity and energy have forged an extended truce. Perhaps a place like this. It's one of the smallest and dimmest stars in our universe, and yet brown dwarfs have been shown to harbor planets close enough to bask in their dim rays. Brown dwarfs, and their hotter cousins, the red dwarfs, form the vast majority of stars in our galaxy. Because they burn so slowly, they will be the final beacons of the majestic age of stars, an era that will extend out to 100 trillion years. Even as galaxies like ours grow dim, another process will begin to transform them. Over time, chance encounters between objects will perturb their orbits, sending some towards the centers of those galaxies, and others flung out into the void. In this way, galaxies may gradually evaporate, with ever more dense concentrations of matter accumulating in their cores. The universe now begins to take on a new character. Welcome to the degenerate era, in which the cosmos is populated by red and white dwarf stars, steadily cooling, and by the charred remains of supernova explosions, the neutron stars, and black holes, slowly spinning down. Even though these dead stars have used up their nuclear fuels, the universe continues to produce small amounts of energy. They scoop up and annihilate dark matter particles that manage to stray into their grasp. Now here is where change slows to a crawl. It's expected that protons, the building blocks of all atoms, will slowly degrade, turning back into subatomic particles that then decay into photons, particles of light. All the protons in the universe date back to the earliest moments. Their decay marks the end of the degenerate era, around 1 billion, billion years after it all began. That's a 1 followed by 40 zeros. Our picture of what happens after that will come to depend on what we learn in the next few years beneath the border of France and Switzerland, in one of the largest physics experiments ever undertaken. 100 meters underground, the Large Hadron Collider was built to accelerate particles in opposite directions through a ring of tubes 27 miles around. When they reach nearly the speed of light, scientists bring them into ferocious collisions. One goal: to define the final time horizons of our universe and the final moments of one of its most persistent objects. Black holes, ranging from millions to billions of times the mass of our Sun, occupy the centers of most large galaxies today. As those galaxies age, much of their mass will spiral toward the center. And over trillions of years, that mass will fall into ever more ravenous black holes. Conceivably, these ultramassive black holes could end up weighing as much as a galaxy. When they finally stop growing, will they too be subject to the ravages of time? According to the physicist Stephen Hawking, the answer is yes. He proposed a theoretical process of decay that scientists are hoping to test in high-energy particle collisions at the Large Hadron Collider. The idea is that throughout the universe, particles of opposite charges constantly well up in the vacuum of space. They normally destroy each other, but when this happens at the event horizon of a black hole, one particle can be pulled in, while the other escapes. That has the effect of slowly siphoning energy and mass from the hole. If this is true, then even black holes are eventually doomed. But finding out for sure is not easy. Creating a micro-black hole, it seems, will take more energy than any earthbound collider yet conceived can pack. That is, unless there's more to our universe and to gravity than we've thought. The key lies in whether the world we know is part of a more complex cosmic reality, beyond the 3 spatial dimensions plus time that we experience in our daily lives. If so, we would be like insects living on the 2-dimensional surface of a pond, completely unaware of the deep and complex reality below us. It may be possible that one of these extra dimensions could intersect our universe on an extremely tiny scale. According to some scientists, when particles collide at very high energies, the additional gravity needed to create a micro-black hole could come from this extra dimension. They'll know a black hole is there when they see the shower of particles predicted by Hawking's theory. That shower will open a brief window into a deeper cosmic reality, while shedding light on the ultimate future of our universe. Based on Hawking's theory, the last black holes will disappear when the cosmic clock strikes 10 to the 100th years from now. That's a number known as a googol. That's the end of our universe, and yet it's still far short of forever. What will happen, say, in 10 to the googol, a googolplex years? Well, if you wrote all those zeros out in tiny 1-point font, it would stretch beyond the diameter of the observable universe. Will the great arrow of time ever come to rest? Or does that arrow fly a curved path, destined to cycle back again and again, as whole new universes come into being in a way similar to our own? The numbers that describe the time horizons of our universe are incomprehensible, yet they may well be relatively insignificant in the grand scheme of things. Earth and humanity are products of the great era of stars, and we have been witness to its great spectacles of gravity and energy. Yet it's fair to say that we occupy a truly tiny period within the vast cosmic sweep of deep time. And we can easily imagine there are others out there, somewhere, who also look out and attempt to comprehend the changes they see. They too may invent the idea of time and develop their own theories on where it's all leading. Will their discoveries, and ours, somehow survive as we all gradually go the way of the stars that made life possible?